Hello, in this video we're looking at using the binomial distribution, and this is for learning intention 42, and this will be part 1. So this will be an introduction, try to get you to feel comfortable about these problems and understand where they come from. And I think the best way to explain it is chocolate bars. So I remember we lived at a milk bar at one stage, and I remember the free bars promotion for Mars. So remember, they would have said that 1 in 6 bars wins free. Great. That got me thinking. I was like, hang on, if I buy 6 bars, does that guarantee I win 1? But then I thought, well, no, because I can lose 6 times if I buy 6. There's nothing saying I won't lose every time. But then I thought, but if I buy more bars, I'm more likely to win. So this is the first time I ever thought about this problem, and it turns out some brothers, they would have been about the 18th century, they were the Bernoulli brothers. They were a family, and maths was their trade. Maths is what they did, and they formalized all of this. So the first thing I'm going to do is give you an example where we analyze it with the maths we already know, and then we're going to analyze it using something called Bernoulli trials, and that's going to simplify things. So I want to know, if I buy 3 bars, what is the probability that I win exactly once? What's the probability I win exactly once? Is it going to be more than if I buy 1 bar? I think so. Well, let's analyze it. And if we don't know binomial distributions, well, the only tool I can think of to use would be a tree diagram. So let's draw a tree diagram. You buy your first bar, and there's a 1 in 6 chance that you win. Yes, free bar and diabetes. And a 5 in 6 chance you lose. There we are. Okay, then you buy another bar, and 1 in 6 wins free, but 5 in 6 lose. And the same over here, 1 in 6 wins free, 5 in 6 lose. Okay, then you buy another bar, win, lose, win, lose, win, lose. 1 in 6, 5 in 6, 1 in 6, 5 in 6, 1 in 6, 5 in 6, 1 in 6, 5 in 6. Alright, I'll give you a moment to copy that down while I slurp my tea. Alright, let's go through. So we're going to have win, win, win. Win, win, lose. Win, lose, win. Win, lose, lose. Win, lose, lose. Lose, win, win. Lose, win, lose. Lose, lose, win. And lose, lose, lose. So those are our 8 possibilities. So which ones are winning exactly once? That's winning exactly once. That's winning exactly once. That's winning exactly once. Any others? No. So the probability of winning exactly once equals, well, it's the probability of winning, which is 1 in 6, times the probability of losing, which is 5 in 6, times the probability of losing, which is 5 in 6, plus the probability of losing times the probability of winning times the probability of losing, plus the probability of losing times the probability of losing times the probability of winning. And I want you to notice something here. look what's happening. The 1 in 6 just moves along one, doesn't it? It moves along to there, then it moves along to there. So let's calculate this. This is 25 on 216, and these are going to have to be the same because of the commutative law of multiplication. 25 on 216 plus 25 on 216, which is 75 on 216. So let's think about that. 1 in 6. Well, yeah, you're more likely to win exactly once if you buy 3. Not necessarily intuitive, but that's the probability of winning exactly once if you buy 3 bars. Let's try to simplify it. I'm pretty sure 3 goes into both of those. So that goes to 25 and 72. Can anyone simplify that further? No, that's your answer. 25 on 72, so it's roughly about a third of winning exactly once. That's not intuitive. I mean, you know, how are you meant to just know that? Oh, and I circled, yep, win, win, win. So there you are, 25 out of 72, about a third. That's all well and good, but look at this. The 1 on 6, I mean, it occurs 3 times. So I know exactly what you're thinking. You're thinking, hang on, combinatorics. Another way I could write this would be 3 choose 1, because how many ways can I choose one winner from 3 times probability of winning times the probability of losing times the probability of losing. That's another way of writing this. That's very interesting, because we can take all of this and we're going to put it into a formal language that's going to simplify our analysis. So it might look intimidating at first, but I'm going to clear this and we're going to analyze this Mars bar problem without tree diagrams. We're mature mathematicians now. We're going to use abstract symbols and we're going to be comfortable with this. Okay, this topic is called Bernoulli trials. And the Bernoulli brothers were very arrogant. They were very rude people. So Bernoulli trials. And this ties into discrete random variables. So we say that a discrete random variable, x, is binomially distributed, is binomial, with n being the number of trials and p being the probability of success. Don't worry, I'm going to break it down. So this is what you need to be a binomial distribution. You need 2 features. If you want to be a binomial distribution, you need 2 features. So you have to have some trials, flipping a coin, buying a Mars bar, whatever. You have to have some trials. And it has to be a win-lose situation. A win-lose situation. You either win or you lose. You're on or off. It's black and white here with binomial distributions. So it has to be a win-lose situation. Success or failure. Has to be a situation like this where the probability of success stays constant. So it doesn't change after each trial. Like with the Mars bars, it's just 1 in 6 wins free. And now you could argue, well, if you draw out a Mars bar, it's, you know, there are less winning Mars bars, so it's slightly different. But no, we're just going to say a probability of success is some constant number. So we need to have trials. You either win or lose, and a probability of winning is a constant value. Alright, how do we use this to analyze the Mars bar problem? I'm going to write the problem again. So the problem was, if I buy 3 Mars bars, what's the probability of winning exactly once? Alright, how do we analyze this? Well, there's actually a formula. which breaks this down. So we're going to define x as our random variable. It's binomial because we have a number of trials, which is 3, and we have a probability of winning. So x is binomial. It's a discrete random variable, which is binomial. We're doing 3 trials of this game, buying a Mars bar, and we have a probability of success of 1/6. So it's binomial. Alright, so what's the probability of winning exactly once? Here's where the formula comes in. So this is a definition here. We're defining x as a discrete random variable to be binomial, where there are 3 trials and a probability of success is 1/6. Alright, here's the formula. Here's the thing you need to know. So the probability that x, our discrete random variable, equals 1, so that we win exactly once, is, and in fact, no, I'll write the formula first. I'll write the formula. Probability of x equaling x is the number of trials choose x times the probability of success to the power of x times the probability of failure, which is 1 minus the probability of success, to the power of n minus x. If that looks intimidating, don't worry, it was just the exact same problem before. This is the exact same problem before. If you like, this is every possible tree diagram without replacement. It's much nicer to write this than massive tree diagrams. You'll learn to love this, guaranteed. So the probability that x equals 1, that we win exactly once, equals the number of trials, which is 3, choose 1, we win exactly once, times the probability of success, which is 1 in 6, to the power of 1, times the probability of failure, which is 1 minus 1 on 6, to the power of 3 minus 1. Let's tidy that up a bit. So it's 3 choose 1 times 1 on 6 times 5 on 6 squared. So that's the exact same thing we had before. Look at your notes before. 3 choose 1 is 3. So it's 1 on 6 times 5 on 6 times 5 on 6 3 times. That's what this is saying. So this formula here, which is just beautiful, is every tree diagram without replacement. You could have 100 trials. In fact, we could do that next. You could have 100 trials. So let's work this out. 3 choose 1 is 3 times 1/6 times 5/6 squared, and we should get the same number. So we have a half times 25 on 36, which is the same answer, 25 on 72. There's our answer. So that's the probability of winning exactly once. We could work out the probability of winning exactly twice. We'll just replace the x with 2 there. Shall we do that? Shall we see what happens? Let's do that. What's the probability of winning exactly twice? Isn't it nice? You don't have to draw tree diagrams anymore. You are now mature mathematicians. So the probability of winning exactly twice is 3 choose 2, 1 on 6, to the power of 2, 1 minus 1 on 6, to the power of 3 minus 2. What's 3 choose 2? Well, it's 3. You can use Pascal's triangle if you're unsure. 1 on 36 times 5 on 6 to the power of 1. So that becomes 15 on 216. And can we simplify that? Yep, we can divide the top and bottom by 3, so we get 5 on 72. There you are. You're much less likely to win twice. What's the probability of winning 3 times? Well, one way to work it out is 1/6 times 1/6 times 1/6. So we know that it's going to be 201 on 216. But let's check it. Let's see if the formula checks out. What's the probability of winning exactly 3 times? Well, it's 3 choose 3 times 1 on 6 to the power of 3 times 1 minus 1 on 6 to the power of 3 minus 3. 3 choose 3 is 1 times 1 on 216, and that's going to be 0, so anything to the power of 0 is 1. There you are, the formula checks out. It's 1 on 216. That's the binomial distribution. In the next video, we'll look at how to look at some examples from the next exercise just to get you rolling. And if you have been, thanks for watching.